All right, so when you apply the finite element method, ultimately you always come out with a linear system. Even if you have a nonlinear problem, you apply something like a Newton's method, for example, and then in every Newton step you have to solve a linear system. So what I would like to talk about in this lecture is, what do you actually do with this linear system? What are the methods that you can apply? So I would call this what solver to use. This is sort of a piece of practical advice. So when you apply the finite element method, you come out with a linear system, let's say ax equals b. And what do we know about these linear systems? Well, typically they're large, right? We want to solve 2D, 3D problems with maybe a few hundreds or a few thousands or maybe a few million cells. So typically you come out with a linear system that has maybe a few thousand to up to a few billion unknowns. So some of these systems become very, very large. If you solve, let's say, on 1,000 by 1,000 by 1,000 three-dimensional mesh, you already have a billion nodes, and that might mean a billion or more unknowns. Okay? So these matrices are very large. Typically, however, they're rather sparse. If you think, for example, of the Laplace equation in 2D, you have probably heard of the 5-point stencil. So in this case, every row of this matrix would have only 5 entries. For typical finite element methods for more complicated problems, let's say for the Stokes equation, you have, of course, more than 5. So let's say for a typical Stokes discretization, you have maybe 100 or maybe a couple hundred entries. But be that as it may, you typically have a relatively small number of entries per row, so the matrix is sparse. Typically, however, it is ill-conditioned. The condition numbers can be up to 10 to the 9, for example. And we know, for example, for the Laplace equation, that the condition number grows like h to the minus 2. So every time I make the mesh finer by a factor of 2, the condition number grows by a factor of 4. So the question then is, I have this linear system, and what do I actually do with it? Of course, if you are using MATLAB, for example, for small enough problems, you would just use the backslash operator, but for, let's say, realistically sized problems, that's just not an option. So let me walk you through the options that you have. And basically, there are 2 alternatives. You can either use a direct solver, or you can use an iterative solver. Let me first describe to you a little bit what these actually are. So direct solvers, you can think of them as follows. So you've seen in your basic numerical methods classes how to compute something like an LU decomposition. So an LU decomposition is, I give you a matrix, and you come up with 2 matrices L and U, so that the product of L and U equals A, and so that L is lower triangular and U is upper triangular. And we want it this way because then I can solve a linear system AX equals B by one forward substitution and one forward elimination and one backward substitution step. Okay. Sparse direct solvers do essentially this. So there's a class of algorithms that are called sparse direct solvers that compute factors L and U, and that do this in such a way that they respect the sparsity pattern of A. So it's not difficult to show that even if A is a sparse matrix, L and U are typically not sparse. But we can do it in such a way that L and U are also not matrices that are completely full. So we can find a compromise where L and U save some of the memory. So let's say only 10% of the matrix actually is occupied, whereas the remaining 90% is empty, it's just zeros. So sparse direct solvers use the sparsity of this matrix A to come up with factors L and U that are easier to compute and easier to store. And in particular, if you look at the amount of work that you have to do for typical partial differential equations when you want to compute an LU decomposition for a matrix A, would be that the work grows like n to the power of 1 plus 2 d minus 1 over d, where d is the space dimension. So in 2D, the work actually grows only like n squared. Whereas you know that if you do an LU decomposition for any dense matrix, the work would actually grow like n to the 3. Okay, so using the sparsity of these matrices helps you to save 1 power of n in the amount of work in 2D. In 3D, this looks a little bit different. In 3D, it's n to the 7 over 3. And I don't want to go into the details why that is so, but it's not all that difficult to understand where that comes from. It's basically because the bandwidth of matrices in 3D is much larger than in 2D. The amount of memory that you need to store grows like n to the 1 plus d minus 1 over d. So in 2D, the amount of memory to store the L and U factors is n to the 3 over 2, and in 3D is n over 4 over 3, when we know, for example, that in order to store the LU factors for a full matrix, of course, takes exactly as much memory as to store the entire matrix A. So the amount of memory that you would take for a full matrix would be n squared. Here I have only n to the 3 over 2 in 2D and n to the 4 over 3 in 3D. So I need much less work and much less memory to compute these L and U factors for a sparse matrix. Okay? Not optimally less, but certainly I can make use of the sparsity. So these sparse direct solvers have the advantage that they're very robust. They always work. And I'm going to use that later on when I give you a little bit of advice of when to use them. Always work means I give it a matrix and it just computes these factors and it solves the linear system for me. That is something that is not as easy to achieve for iterative solvers. So for direct solvers, there are a number of high-quality open-source packages. There's, of course, a million packages out there on the internet that you can download, but there's a number of high-quality packages. The most widely used ones are called UMFPAC. Then there's one that's called SuperLU, and then there's one called MUMPS. The latter two are even parallelized, so you can use them on relatively large problems. Let's say if you can use them certainly on tens of millions, hundreds of millions of unknowns if you need to, if you have sufficiently many computers around. The advice that I want to give you, just like for all of the other software packages that we talked about, let's say visualization software, finite element software, and so on and so forth, is even though there are a million packages out there, the number of really high-quality maintained ones is not that large. And my advice is go with the high-quality ones that I listed, that are well-tested, that are widely used in the community, where people have sort of an idea of how they perform, where you can find help in the community. So don't just go out, download the first thing that you find, but use something that is known to widely work. The alternative to direct solvers is what we call iterative solvers. And I'm sure you have heard the basics of this. Basically, the idea of iterative solvers is something like this. So you start with an initial guess x0 for the solution of ax equals b. And it could, for example, be the 0 vector. And then out of this x0, these iterative methods compute in x1 and x2, x3, and so on and so forth, until some stopping criterion is satisfied. So typically, what these methods do is they keep iterating until the error or the residual in your linear system is less than some tolerance. And then this xk, the final guess, is returned. Now, there are a number of things that you need to know about iterative solvers. First, in the very best case, some of these iterative solvers can solve a linear system in O of n operations if this matrix is sparse. And that's sort of a miracle in itself, because if you think about it, if you wanted to solve a dense linear system, then to just do one matrix vector multiplication requires n squared operations, right? Because the matrix has n squared entries. So the fact that in some of these methods you can solve a linear system in O of n operations means that you can definitely not, or that you cannot hope for this to be the case for a full matrix. O of n is an effort that can only be achieved if a matrix is sparse. And that means you only ever multiply the non-zero entries, and you never multiply with the zeros, because if you did, you would immediately have a complexity O of n squared for just one matrix vector multiplication. So the optimum complexity of some of these would be O of n. That depends on what kind of iterative solver we have and what kind of preconditioner we have, and I'm going to come back to the question of preconditioners later. Sometimes the actual complexity is much worse than this. So if we don't have a good preconditioner, for example, you might end up with something that has a complexity that is on the same order as, let's say, for direct solvers, or even worse. On the bright side, the amount of memory that you need is typically O of n. So typically you store, let's say, the solution vector and maybe a handful of temporary auxiliary vectors. But in any case, each one of these vectors has n entries, and so the overall memory consumption is O of n. And that's certainly a big advantage over sparse direct solvers. So sparse direct solvers are good because they're robust, and oftentimes they're pretty fast too, but they run out of memory. So if you have a problem with, let's say, 10 million unknowns, then that's not something that's very difficult to solve using an iterative solver, but it is actually very difficult to solve using a sparse direct solver because you run out of memory. So that's the limiting factor for sparse direct solvers. The other thing that I want to point out is that iterative solvers do not solve the linear system AX equals B exactly, but what you get is a guess xk that is only an approximation to this exact x here. And all of these iterative solvers have a stopping criteria that you can tune, so you can make this xk come closer and closer, or as close as you need it to be, to the exact solution x of this linear system. Of course, in practice, this doesn't really matter that much because you get this linear system out of a finite element discretization that has a discretization error. And as long as you can make sure that the iterative solution of AX equals B is no less accurate than the discretization error, you're fine, right? It doesn't make any sense to put a lot of effort into the exact solution of a linear system if you know that the exact solution of the linear system only yields an approximation to the partial differential equation. You just have to balance these sort of errors. All right, so what iterative solvers exist? There's a wide variety of solvers that are called CG, that's conjugate gradient, min-res, GM-res, and so on and so forth. Almost all of them are actually rather simple to implement, and that's a big difference to the sparse direct solvers. Most of them require no more than 200 lines of code. So there's a large number of fairly high-quality implementations. Among the advantages of these methods is that, by and large, you only need a multiplication operation with the matrix. And I've shown you this when we solved step 20, where all we needed is I give you a vector, and you give me the product of this matrix with this vector. Whether you have the actual entries of this matrix at hand, if you can tell me what the entry M25 or A25 is, that's not important for me. All I need is that I can give you a vector, and you return to me the product with this matrix. And so it allows for many more powerful schemes than a sparse direct solver. A sparse direct solver really needs the entries. So a Schur complement, for example, cannot be solved with a sparse direct solver, but it can be solved with an iterative solver. The disadvantage of iterative solvers is that typically the efficiency of these methods hinges on the availability of good preconditioners. And like I say, I'll come back to the question of what a preconditioner actually is at a later time in the next lecture. But I do want to make the point that it's not the iterative solver. It is not whether we use CG or min-res or GM-res that determines how fast we can solve a linear system, but it is the preconditioner that makes a difference, not the solver. Okay, so how do you choose between direct and iterative solvers? The first consideration you should have is this. So when you write a new program, there are essentially two possible sources of error. A, you might not assemble the right linear system, or you might not solve the system correctly. And the first version of every program is always buggy. So when you want to figure out what the problem is, you should just eliminate one of these possible sources of errors. And as long as your problem is small enough, the approach to this would be like this. Use a direct solver, okay? Because the direct solver always works. We know they work. They're very robust. You can rely on these packages to be correct. And so in other words, if you use a direct solver, you have already eliminated the second possibility for an error. if you get the wrong solution with a direct solver, you know your discretization or your assembly is wrong. Once you have shown that the assembly is correct, that the linear system is correct, and that you get the right solution, then you can think about an iterative solver. So this is sort of the general approach I always recommend. You start with a direct solver. When you know it works, then you switch over to an iterative solver. If you want to see how to do this, step 29, for example, has an example of where we use a direct solver. The other sort of consideration you might have for this trade-off between direct and iterative is this. So direct solvers always work. You don't need to think about preconditioners. You don't need to think about which solver to use. They always work. They're also, and that's something that we don't often talk about in numerical methods classes, they're actually faster for most problems that have less than 100,000 unknowns. So typically, we teach our students that iterative solvers are so much better because, let's say, they're more elegant than this old Gaussian elimination scheme that we use for LU decomposition. And we think of them as sexier. But it turns out that for problems of very moderate size, let's say 100,000 unknowns, which covers most of what we want to do in numerical methods research today or in solving real problems, direct solvers are actually faster. And so if your problem has less than 100,000 unknowns, my recommendation would be just use a direct solver. There are, of course, downsides to direct solvers. In particular, if you have larger problems, then you need too much memory and too much CPU time. And so for larger problems, you cannot use direct solvers efficiently or at all. And in that case, you need to use iterative solvers. We know that they need OFN memory. We know that they can solve very large problems. So we have solved problems with billions of unknowns with iterative solvers. They often also parallelize relatively well. So if you have, let's say, 1,000 computers and 1 billion unknowns, you can solve your problem in parallel on these machines. The downside to iterative solvers is that the choice of the preconditioner and the solver depends very much on the problem. So you have to have a lot of insight into the kind of matrix that you have, into the structure of the matrix, what the problem is that it comes from. That determines which iterative solver to use. Like I say, so my advice is if the problem is small, then direct solvers are fast enough and fit into memory. You should use them. Only if the problem is known to have been correctly assembled, is large enough, and or you want to parallelize the solver, that's when you should switch to iterative solvers. Now, when you do want to use iterative solvers, here's a little bit of an overview of what to choose. There is, like I said, a large number of methods. For example, CG, MinRes, GMRes, FGMRes, SimLQ, BiCG, SNAP, QMR, TFQMR. I could go on with this list for the entire day as long as I want. There are many more methods than the ones that I list here. Which one to choose depends on the properties of the matrix, primarily if the matrix is symmetric or definite. And let me give you the rundown which to use when. So if the matrix is symmetric and positive definite, then you should use CG. Conjugate gradient requires the matrix to be symmetric and positive definite, and if the matrix is in fact symmetric and positive definite, then CG is by far the most efficient method. If your matrix is non-symmetric but still positive definite, so for example, if you have an advection diffusion problem where the diffusion is dominant, in that case you would use a method that is called BiCG stab, so for biconjugate gradient stabilized. For all of the other cases, you would use either GMRes, or if you deal with what we call variable preconditioners, you would use something that we call FGMRes for flexible GMRes. And that's really all you ever need to know about iterative solvers. Yes, there are others, but these 3 or 3.5 or 4 are really the only ones that are widely used. And like I said, if you categorize your matrix based on what I have on the right here, choose the solver on the left. That's essentially all you need to know. There are some cases where some of the other methods are useful, But in those cases, you will find this in the literature, or you will know about this. Most of the time, the taxonomy that I just gave you is fully sufficient. The basic rundown of iterative solvers boils down to this one slide, though, namely that if you don't have a good preconditioner, then all iterative solvers are equally bad. You need to have a good preconditioner to make them efficient. Maybe this is something that doesn't bother you so much if you have only 1,000 or 10,000 unknowns, but if you want to solve problems that have a realistic size, let's say 1 million unknowns, 10 million unknowns, or maybe 1 billion unknowns, then all of these iterative methods are equally bad if you do not have a good preconditioner. So the preconditioner really is the key to making iterative solvers work. And basically then what it comes down is that the art of devising a good iterative solvers is devising a good preconditioner. And so what I will come back to in the next lecture then is that I want to talk about, let's say, how do you actually come up with a good preconditioner? What are the strategies for this? What are the methods by which we can identify what is a good preconditioner and what is not? And how do we generalize preconditioners that we know to work well for, let's say, a Laplace problem? How do we generalize these then to also work, let's say, on a Stokes problem, for example? So that's the big question that has kept this field going for the last 15 or 20 years. Since we know what to do for the Laplace equation, how do we generalize this to more complicated problems? So that's what I'll talk about in the next lecture then.